What if every linear function could be represented using an inner product, and every transformation had a natural transpose? Let's explore linear functionals and adjoints. We begin with a simple mapping, a function f mapping a vector space V to its scalar field f. To understand this mapping, we rely on the framework of inner product spaces. These spaces are what allow us to move beyond abstract sets and actually measure the lengths of vectors and the angles between them. When we apply a linear functional in this space, we take a vector as an input and return a single scalar value. It's a way of collapsing a multidimensional vector into a single number. This leads to a specific question. If we fix a vector y and take its inner product against an arbitrary vector x, can that single geometric operation reproduce the behavior of any linear functional we can define? This relationship is formalized by the representation theorem. It proves that every linear functional corresponds perfectly to a specific inner product. The vector y acts as a fixed anchor. The theorem relies on finite dimensions to guarantee this vector exists for every possible functional. We can now extend this from static functionals to active transformations. If we apply a transformation t to x, the result t of x is still just a vector, which we can then pair with y in an inner product. This brings us to the adjoint. We can move the transformation t to the other side of the comma. When it shifts to operate on y, it becomes t star. For any linear operator on a finite dimensional space, mathematics requires this unique operator t star exists. The logic follows a clear path. The representation theorem turns the inner product of t of x and y into a functional, and that functional identifies the unique vector we call t star of y. This makes the adjoint a direct extension of the representation theorem. Think about how this looks in terms of matrices. Is the matrix representing t star always the conjugate transpose A star? That's the common trap. The adjoint matrix and the conjugate transpose A star only align if the basis you are using is strictly orthonormal. Example 17 in the text proves this by using a skewed, non-orthonormal basis. In that case, the matrix representation for the adjoint becomes a complex, non-standard mess that looks nothing like a simple transpose. We also have 4 key algebraic properties that define how adjoints behave. Look closely at the second rule. When you pull a complex scalar c out of an adjoint, you must apply the conjugate bar. Missing this is a very frequent error. To see this in practice, we can look at n by n matrices. By using the trace inner product, we can show algebraically why the left multiplication operator t of x equals ax results in an adjoint of t star of x equals a star x. However, these rules have limits. In infinite dimensional spaces, like the space of polynomials, a differentiation operator often fails to produce an adjoint because the integral required to define it doesn't always converge to a new polynomial. These predictable matrix properties are a specific benefit of working within finite-dimensional orthonormal environments. Let's summarize. First, remember that linear functionals map vectors directly to scalars. Second, the representation theorem tells us these functionals can be perfectly expressed as inner products. Third, the adjoint is the geometric generalization of the matrix transpose. This perspective reveals the matrix transpose as the coordinate-based version of a much deeper geometric symmetry. If you found this helpful, like the video and subscribe for more clear explanations from Hoffman and Kunze linear algebra.